Okay, hello to everybody. We're going to talk about chapter number 6 now. Okay, let me go to the slideshow mode. Okay, chapter number 6 and chapter number 7, they are basically about enzymes. So in these chapters, we are going to talk about what enzymes are, how do they work, and how the enzyme activity um, is inhibited, how it's regulated, all these concepts we're going to talk about. So first of all, what enzymes are? Enzymes are basically the biological catalysts which can actually speed up the rate of reactions. So they can make the speed of the reaction fast. So if we have a reaction which is taking place in the absence of enzyme, that reaction may take millions of years to take place. But the introduction of the enzyme makes the rate of reaction very fast. So mostly when we talk about the biological catalysts, which are basically the enzymes, um, majority of the enzymes, they are protein in nature, okay, and especially the globular proteins. So which we have talked in the last lecture, what are fibrous proteins and globular proteins. So globular proteins are more compact proteins. So these enzymes are globular proteins. So as I said, majority of the proteins, majority of the enzymes are protein in nature, but RNA can also act as enzyme. So they can speed up the rate of reaction, they can make the reactions fast. Okay, so basically how do enzymes speed up the rate of reaction? Okay, so let me talk about the example of a reaction, a reaction in which there are some reactants, and the reactants get converted into the products. So the reactants, they have some energy in them. The products which will be formed, they will also have some energy in them, and that we call it a free energy. So there is a value called delta G. Okay, what is delta G? It's a standard free energy change. So this is the change in energy when the reaction proceeds, and the reactants, they are formed from they are formed into products. So standard free energy change is the difference between the energies of reactants and products under standard conditions. Now for a reaction to take place, there is a requirement of input of some energy. Okay, the reactants, they have some free energy in them, but they require the input of more energy in them, and that energy is called the activation energy. Okay, so the function of an enzyme is to lower the need of activation energy, to make the value of activation energy less. Okay, so basically, as I said, reactants and products, they have some free energy in them, and for a reaction to proceed, there is a requirement of input of some activation energy, and the function of enzyme is to lower the value of, or the amount of, or lower the amount of this activation energy. So that is what the role of enzyme is. And how does enzyme do that? Basically, enzyme provides a kind of a platform on which the reactants can come and sit, and they can react and then form the new products on the enzyme. That's the way how enzyme acts, and it reduces the requirement of the activation energy. So delta G, you should know some values. Delta G, this is the delta G naught is the standard free energy change, and delta G naught with this sign is the activation energy. So delta G, this activation energy for an uncatalyzed reaction is higher than that of the catalyzed reaction. So you can see here, this is a graph which is showing us that this is the free energy of the reactants, and this is the free energy of the products. Okay, so this value, so this is a graph, this is the progress of reaction on the x-axis, and on the y-axis of free energy. This is the free energy of reactants, and this is this value. So this value we can see here on the graph, and this value here on the graph, this is the free energy of the products. The difference of the free energy of the products and the reactants, this value is called delta G. This is the free energy change when the reactants convert into the products. That's called the delta G naught. Basically, that's a free energy change. But for a reaction to take place, there is a requirement of input of energy. So these are the reactants, they need input of energy, Okay, and this amount of energy which is required to be input into the reaction, this energy is called activation energy. Okay, so these reactants, when they get this amount of energy, the activation energy, then they reach to this transition state, and in this state they react and then they form the products. So every reaction needs a input of the activation energy. So what's the function of the catalyst or the biological catalyst or the enzyme? The function of enzyme is to lower this value. So if this is the so this is the free energy of reactants. Up to here is the activation energy. So which means going from here to here, going from here to here, this is the activation energy. So this is the activation energy for the uncatalyzed reaction, and you can see this is the path of the catalyzed reaction. So the catalyzed reaction needs less activation energy, the input of less activation energy. So it's the input of energy, which is the load activation energy for a catalyzed reaction, is going from here up to here. So that's the function of the enzyme. It lowers the activation energy in a reaction. So this is basically showing you this reaction in which hydrogen peroxide is getting broken into water and oxygen, and for this reaction it is showed that it's shown here that this is the activation energy, which this is in kilojoules per mole, this is kilocalories. So you can see that the amount of activation energy which is required for this reaction to take place, if there is no catalyst, it's 18 kilocalories. And if the inorganic catalyst is there, which is platinum surface, it's 11.7 kilocalories. But if the enzyme is there, in this case, for this reaction, the enzyme is catalyst, the activation energy required is 5.5 kilocalories per mole. So this basically shows us that how the presence of the enzyme can lower the activation energy. Okay, so basically, how does the enzymatic reaction takes place? So basically, as we're talking about a reaction taking place in which reactants are converted into products, these reactants are called, first of all, they need to go at a specific region on the enzyme, and that region is called the active site. So active site is that region on the enzyme where the substrate goes and binds. And the substrate goes and binds to the active site by using various kinds of forces, some non-covalent forces including hydrogen bonding, electrostatic attractions, and van der Waals attractions. So there are two models of the, so when the substrate goes and bind to the, so basically overall what happens is the substrate goes and binds to the active site of the enzyme, and there this substrate, there are some bonds in the substrate, they get broken, new bonds are formed, and new products are formed on the enzyme. So there's the catalysis reactions going on the enzyme, and as a result of that the products are formed, and then the products leave the enzyme, and enzyme is actually not used up in the reaction, and the enzyme can be used over and over again. So there are two models basically which talk about the formation of enzyme and substrate complex. First is lock and key model. So according to this model, the enzyme has a very complementary shape to the substrate, and substrate goes and binds there. So substrate binds to that portion of the enzyme with a complementary shape. There is another model for the enzyme substrate binding, that's called the induced fit model. According to this model, the substrate goes and binds to the enzyme, and there are some changes, some conformational changes takes place in the shape of the enzyme, and the enzyme gets a shape, and in that shape substrate can bind in a better way to the enzyme. So binding of substrate induces a change in the conformation of the enzyme that results in a complementary fit. Okay, so this basically shows us both the models. So you can see here, this is the lock and key model. So this is the enzyme, and this is the active site on the enzyme, and you can see this is a substrate, and you can see how the substrate goes and binds on the enzyme. So this is the enzyme, this is the active site on the enzyme, this is substrate, and you can see how the shape of the substrate is so complementary. The shape of the active site and the the shape of the substrate, how well they fit into each other. Okay, and they form this complex. And this is the induced fit. In this, you can see this is the enzyme, and this is the active site, and this is substrate. So substrate is going to go and bind to the enzyme, and then there will be some changes which will be happening in the enzyme, and those changes in the enzyme, those changes in the enzyme will make the substrate fit. Uh, those changes in the enzyme will make the substrate fit in a better way to the enzyme. So basically, if we talk about the energy levels, so basically, first of all, enzyme and substrate, they bind to each other and form the enzyme substrate complex. So basically, you can look here. So this is the enzyme plus substrate. So so when the enzyme substrate complex is formed, it's lower in the energy, lower in the energy levels. So they need to get an input of this much energy, which is the enzyme transition state complex. Like, this is the amount of the energy, the input, this is the activation energy which is required, and then the products will be formed. So this is basically showing you the progress of the reaction. So first of all, substrate goes and binds to the active site of the enzyme, and it forms a temporary complex called ES complex, and then their energy level is low, and they need the input of energy, which is the activation energy, to reach to the transition state. And then this the catalysis reaction will take place on the enzyme, and then from the reactants, or the substrate is a reactant, the products will be formed, and these products then will leave the enzyme. So this is basically showing what I just said. This is ES complex, and here the catalysis reactions will take place, and the products will be formed on the enzyme, and the product is going to release the enzyme. Okay, so this was in general about the how enzymes function, what do enzymes do, how the catalysis reaction takes place. Now I'm going to talk about enzyme kinetics. So in the enzyme kinetics, basically we are trying to understand what is the effect of substrate concentration on the activity of the enzyme. So basically, how much substrate is present and how it affects the rate of the enzymatic reaction, the activity of the enzymatic reaction. And there are some parameters which we are going to measure, and those parameters tell us the progress of the reaction. So basically, in a reaction, when we have some concentration of the substrate and we have some concentration of the enzyme molecules, so initially when we increase the concentration of substrate, the rate of reaction increases. Okay, so initially when we keep on increasing the substrate concentration, the rate of reaction keeps on increasing, but at some point the rate of reaction stops increasing and it becomes constant. Now the reason is that basically, in a reaction we have some substrate molecules, we have some enzyme molecules, and enzyme molecules, they have active site on them. So initially when the substrate concentration is less and there are more enzyme molecules, so the substrate molecules can go and bind to the active site, and there are some active sites which are free. So as we increase the concentration of the enzyme, as we increase the concentration of substrate, all the unoccupied active sites will be occupied by the substrate, and the rate of reaction will increase. So the rate of reaction will keep on increasing till the active sites on the enzyme are free. Once the active sites on the enzyme become occupied, and technically we can call that state that the enzyme is now saturated with the substrate. So beyond that point, even if we add more substrate, because there is no free active site, the rate of reaction is not going to increase, it will stay the same, and it follows a pattern which I'm going to show you. We are going to talk about the Michelson-Milton equation, or the Michelson-Milton relationship, which basically talks about the relationship of the substrate concentration with the enzyme activity. Let me go to that slide and show you, and then I will come back to this example, which is a very nice example to understand. So basically, this is the relationship between the substrate concentration and the rate of the enzyme reaction. So on the x-axis we have substrate concentration, and on the y-axis we have the velocity of the reaction. So you can see here on the x-axis, as we are increasing the substrate concentration, initially, as we are increasing the substrate concentration, the rate of reaction is increasing. Okay, and as we keep on increasing the substrate concentration, you can see it has started becoming constant. Okay, so as we keep on increasing the substrate concentration, the rate of reaction keeps on becoming constant. So at some point, after some point when we increase the substrate concentration, the rate of reaction does not increase. Okay, this is what is basically we are going to talk about. And to give you a very simple analogy to understand the same concept which I'm talking about, and we are going to also talk about this relationship in a mathematical form, because it helps us in finding some of the important parameters which are called Vmax value and the Km value, which we are coming shortly. So before I talk about more in a mathematical form, here's a very good example. Suppose there is one room which is having some peanuts in it, and uh, so the peanuts are representing the substrate, and we have some monkeys, and the monkeys, they are representing the enzymes. So suppose we have a room with the peanuts and we have monkeys, and we open the room, and the monkeys come inside the room. And so when the monkeys enter the room, what are these monkeys going to do? They're going to find the peanuts and they're going to shell them. Okay, so suppose uh, we're going to take this example in three different ways. So first part is, suppose in the room the concentration of the peanuts is 1 peanut per square meter. Okay, and averagely every monkey spends 9 seconds finding the peanut and 1 second shelling it. Okay, so basically every monkey is spending 9 seconds uh, looking for the peanut and then 1 second shelling it. So every monkey is averagely spending 10 seconds in this process. Okay, so which means that these peanuts are shelled at a rate of 0.1 peanut per second per monkey. Okay, and as there are 10 monkeys, we can multiply this value with 10, so the value of shelling is 1 peanut per second. So this is the graph, this is the table which is showing you the same values. Now suppose we increase the concentration of peanuts in the room. Now we earlier it was 1 peanut per square meter, now we make it 3 peanuts per square. Now because the peanuts have increased 3 times, the monkey is going to spend 3 times less. The monkey is going to spend 3 times less time to find the peanut and then shell it, which means that averagely every monkey is now using 4 seconds instead of 10 seconds in finding the peanut and shelling it. So which means that the rate of the shelling is now 0.25 peanut per second, and because we have 10 monkeys, the rate of shelling is 2.5 peanuts per second per monkey, for all the monkeys, sorry, for the 10 monkeys we have. So now, so you can see that the rate of shelling per monkey in the first case was 0.1, and when we increase the peanuts 3 times more, the rate becomes 0.25, and the total shelling rate is in this case 2.5. So now we know that we have actually increased peanuts from 1 to 3 times more. Now suppose we make this room full of peanuts. Okay, so suppose we make the whole room full of peanuts, so which means that the monkeys do not need to spend any time in finding the peanuts, because the peanuts are in front of them. So basically in this case, every monkey is going to spend at least 1 second in shelling the peanut. Now the monkey in this case, so basically peanuts are our substrate in this example. We are increasing the concentration of substrate. We have increased from 1 to 3, and now we are making the room full of peanuts, so that the monkey doesn't need to spend any time in finding the peanuts. But in the last case also, the monkey still needs to spend 1 second in shelling the peanut, which means that we cannot reduce that 1 second time. So which means the overall rate of shelling will be 10 now, right? So by increasing the substrate concentration, we have increased the rate from 1 to 2.5 to 10. So can even after that we put more peanuts in the room, can we increase the shelling rate? No, we cannot, because 1 second we cannot take away, right? That is required. So which means that so this is basically an analogy to understand how it's the same analogy that how the substrate concentration affects the um, rate of reaction, enzymatic reaction. So first it increases in a linear fashion, and after some point, even if you increase the substrate concentration, the rate of reaction does not increase. So this is basically an analogy to explain how the enzymes um, activity depends on the substrate concentration. So most enzymes display, this is called Michelson-Menten kinetics. So this is Michelson-Menten kinetics. Okay. So this is all what I just said is written. So the rate of change in product concentration per unit time depends on the substrate concentration. At low S, at lower concentration of the substrate, doubling the substrate will double the rate of reaction, but as substrate concentration increases, each additional increase in substrate results in smaller increase in the velocity. When substrate becomes very large, the value of substrate, when S becomes very large, the value of velocity reaches a maximum. So initially when you increase the substrate concentration, the rate of reaction increases, but as we keep on increasing more substrate concentration, the rate of reaction becomes constant. It does not increase after that point. And at this point, the rate of reaction has become maximum, and this value is called Vmax. Okay. And there is one value which is called Km value. Km value is that substrate concentration at which the rate of reaction is half the Vmax value. So Vmax is the maximum rate of reaction. Km is that substrate concentration at which the rate of reaction is half the Vmax. So this is all what I said. It's all written here. I'm just not going to repeat it. So basically, according to the Michelson-Menten equation, so this is the Michelson-Menten equation. So this is all we're talking about, Michelson-Menten kinetics. So when so it is talking about an enzymatic reaction. When the site of the enzyme, it forms enzyme substrate complex, and then this enzyme substrate complex. So on the substrate on the enzyme, the catalysis is going to take place. It's going to form enzyme and product. So to find the rate of reaction at any point, this is the formula to use, and this is also called Michelson-Menten equation. V is the rate of reaction is equal to Vmax multiplied by the substrate concentration divided by Km plus substrate concentration. And what is Km? This is called Michelson constant. This is the concentration of the substrate where the rate of reaction is half the Vmax value. The concentration of substrate that gives half maximum velocity. So we are going to understand the meaning of these two parameters, which are very, very important, Vmax and Km, because they give us a lot of knowledge about the state of the enzymatic reaction. So we are going to consider three cases. Suppose the first case is when the concentration of the substrate is very low. Okay, so which means we are talking about this place. Okay, on the graph we are talking on this place when the substrate concentration is very low. So when the substrate concentration is very low, which means that this value is very, very small as compared to Km value. So coming back to this Michelson-Menten equation, V is equal to Vmax multiplied by S divided by Km plus S. So which means that this value is very, very small. When this value is very, very small, which means we can ignore this value. So the relationship becomes V is equal to Vmax multiplied by S divided by Km. Okay, so which means that if we look at this formula now, V is equal to Vmax multiplied by S by Km. So at a very, very low concentration of the substrate, okay, the rate of reaction is directly proportional to the concentration of the substrate. So that is what is happening. So at a very low S, the initial velocity is roughly proportional to S. So this is what is happening here. So at this point, when the rate of when the concentration of the substrate is very low, the rate of reaction is increasing. It's directly proportional to the substrate concentration. The second case is very high substrate concentration. Now when the substrate concentration is very high, so which means that this value is very high as compared to Km. Now at this point, when the substrate concentration is very high as compared to Km, which means Km is very small and we can ignore it. So coming back to the same equation, because the substrate is very big, now we can ignore Km. So V is equal to Vmax multiplied by substrate divided by substrate. We are ignoring this value now because this is very small. So the equation becomes V is equal to Vmax multiplied by S divided by S, and we can cancel the X. So when the the equation becomes V is equal to Vmax. So which means that when the substrate concentration is very high, when the substrate concentration is very high as compared to the Km, V is Vmax. So coming back to this graph, so when the substrate concentration is very high, we are here. When the substrate concentration is very high, the rate of reaction is Vmax. Okay, now let's talk about the third case. An also important thing to know about here is when the rate of reaction has reached to the maximum, when the rate of reaction has reached to this point, at this point means this is the maximum rate of reaction. At this point we cannot increase the rate of reaction. The only thing we can do here is by increasing the substrate concentration, we cannot increase the rate of reaction. At this point, the only way to increase the rate of reaction will be to add more enzyme. And the third case I'm going to discuss is, so this is what I just said. So the only way, so at this point the only way to increase Vmax is to increase the enzyme concentration. So this is basically showing the relationship between Vmax value and the enzyme concentration. They have a linear relationship. And third case is when the substrate concentration is equal to the Km value. So at that point, coming back to the formula, V is equal to Vmax multiplied by S Km. So at this point, when the S is equal to Km, at this point we can substitute Km with the S. So then we have 2S, it becomes 2S. So V is equal to Vmax multiplied by S divided by 2S. So this way this crosses with this and the value becomes V is equal to Vmax divided by half. So when the substrate concentration is equal to the Km value, at that point the rate of reaction is half the Vmax value. Going back to the graph, so you can see here this concentration of the substrate is called Km. At this concentration the rate of reaction is half the Vmax value. This is Vmax, this is half the Vmax. So this is the way we can understand Km and the Vmax in a mathematical way. So Vmax basically tells us the maximum rate of reaction, and Km tells us, Km is that concentration of the substrate where the rate of reaction is half the Vmax, and the lesser the Vmax, the more the enzyme is efficient. So lower the Km value for a given enzyme and substrate, the lower the S range in which the enzyme is effective. Okay. Vmax is important as a measure of the potential maximum rate of reaction. So Vmax tells us what is the maximum rate of reaction an enzymatic reaction can achieve, and Km is that substrate concentration at which the rate of reaction is half the Vmax. So lower the concentration of the substrate, so lower the Km, so lower the Km, which means the enzyme needs less substrate concentration to reach the half the maximum rate of reaction. And by the graphical graph, we cannot by this Michelson-Milton graph, we cannot, by this relationship, we cannot calculate the Vmax and the Km values by this kind of a graph. So for achieving that, for calculating the Vmax and the Km value, we basically make use of a double reciprocal plot. So what is done in this is basically both the sides of the Michelson-Milton equation, they are inversed, and the equation is then called Lineweaver-Burke equation. This is the what the equation is. So if you look at this, this is the Michelson-Milton equation. So inverse it, and then we get the Lineweaver-Burke equation. So this is 1 by V is equal to Km plus S divided by V max multiplied by the S. So this can be broken, the equation can be broken like this. So Km V max, so we can basically break this equation into Km divided by V max into S plus S divided by V max into S. So we can, this is called Lineweaver-Burke equation. And basically on the x-axis we plot 1 divided by S. In the Michelson-Milton it is S, here it is 1 divided by S. And in the Michelson-Milton equation, it is in the Michelson-Milton relationship, it is the rate of reaction which goes on the y-axis, but here in the double reciprocal plot it is the inverse of the rate of reaction. This is 1 divided by the rate of reaction. So when we plot the inverse values on this, we get a straight line like this, and this is the slope of this line, which is Km divided by V max, and we can extrapolate this line, and where this line touches the y-axis, that is called y-intercept, and where this line touches the x-axis, it is called x-intercept. And the values of y-intercept is equal to 1 divided by V max. So if we know the y-intercept, we can calculate V max value. And similarly, this point is called x-intercept. X-intercept is equal to minus 1 divided by Km. So if we know the x-intercept, we know the Km value. Okay, so now we are going to talk about the inhibitors. So enzyme inhibitors are those which can inhibit the enzyme activity. So in which situation we want to inhibit the enzyme activity? So enzymes are good for us because they are actually catalyzing the reactions. They are speeding up the rate of reactions. They are accelerating the reactions. They're making the rate of reaction fast. So why should we want to stop their activity? Why should we inhibit them? So there are various situations in which the enzymatic activity is not desirable, where maybe like in cancer, there is an overexpression of the enzymes, and those enzymes are actually making the cells divide abnormally. In that situation, we want to inhibit the enzyme activity. So in that situation, we would like the enzyme not to work, because the overexpression or the abnormal activity of the enzyme is actually making the cells divide. Then some of the antibiotics like penicillin, it is also an enzyme inhibitor. Some of the toxins like potassium cyanide, it is also a enzyme inhibitor. Okay, so various drugs, poisons, cancer drugs, they're all enzyme inhibitors. So antibiotics like penicillin, it kills the gram-positive bacteria. So basically how the antibiotic kills the gram-positive bacteria, because it goes and inhibits an enzyme in the bacteria which is responsible for the formation of its cell wall. So that is, in that case, we are inhibiting the activity of the enzyme, and so in that case, the inhibition of the enzyme activity is a desirable thing. Okay, so if you talk about the inhibitors, there are two kinds of inhibitors. They can be irreversible inhibitors. Irreversible inhibitors are those inhibitors which go and form a covalent bonds with the enzyme. When they form the covalent bonds, I hope you guys know what the covalent bonds are. They're very strong bonds. So if it goes and form the covalent bonds with the enzyme, then enzyme will never be regenerated. So it's a permanent bond with the inhibitor, so enzyme can never be used. Penicillin is a irreversible inhibitor. Then there are reversible inhibitors. Reversible inhibitors are those inhibitors which can go and bind to the enzyme, and they can also leave the enzyme, so the enzyme can be regenerated and the enzyme can be reused again. And among the reversible inhibitors, we are going to talk about competitive inhibitors, non-competitive inhibitors, and the uncompetitive inhibitors. Okay, so first of all, we are going to talk about the competitive inhibitors. So competitive inhibitors are those inhibitors which go and bind to the active site. So you can see here, this is your enzyme, this is the, suppose this is the active site, here the substrate comes and binds. Now competitive inhibitor will be that inhibitor which will come and bind on the active site. Now because the inhibitor is sitting here now on the active site, there is no place for the substrate to bind. So when the substrate is not going to bind, no reaction will take place. So this is an example of competitive inhibitors. So here also you can see, this is the enzyme, this is the active site. Okay, the substrate comes and binds here, and the products are formed. This is which is happening. But now, because of the presence of the competitive inhibitor, the competitive inhibitor comes and binds on the active site. Okay, now because the competitive inhibitor is binding on the active site, there is no room for the substrate to come and bind. So if there is so because the inhibitor is sitting on the active site, there is no room for the substrate to come and bind, and as a result of that, no reaction will take place. Then the another example is non-competitive inhibitors. Non-competitive inhibitors are those inhibitors which do not pose any competition for the substrate because they do not bind to the active site. So what do? They bind to the site other than the active site. So you can see here, this is the active site, this is the another site. So if there is no inhibitor, the substrate is going to go and bind here. The substrate is going to go and bind here, and the products are going to be formed. But in the case of non-competitive inhibitors, the inhibitor goes and binds to the site other than the active site. You can see it's not binding to the active site. Now because of the binding of the inhibitor to this site, the shape of the active site changes, and as a result of that, what happens is, even if this active site is not occupied the inhibitor, this active site is all free, but still the substrate cannot come and bind because that shape complementation is gone now. You can see how the shape was earlier, how the shape is now. So it cannot come and bind here. So this is the way non-competitive inhibitors work. And the uncompetitive inhibition, inhibitor goes and binds to the enzyme and substrate complex. And irreversible inhibitors, I have already talked about. They are the ones which form covalent bonds with the enzyme, and as a result of that, the enzyme gets permanently inactive. It cannot be regenerated. And I give you example of antibiotic, which is a example of an irreversible inhibitor. So this is all about chapter number 6, and we are going to talk about few more things in the next chapter, chapter number 7. We are also going to talk about enzymes there also.